In section 9, we're going to begin our discussion in terms of hypothesis test. And we will focus in this introduction to hypothesis testing on the idea of situations where our test is based on a single sample. So we will be testing both the mean and a proportion in this section. So the first thing you have to know is just really the basic setup of a hypothesis test and where the errors come from. So there are really two main forms of inferential statistics that we focus on, which is the idea of a hypothesis test, which we're going to learn about in this section, and then the idea of a confidence interval, which we talked about in the last section. So I'll also show you a little bit of the overlap between those two. But when you think about a hypothesis test, there's also error like there is in a confidence interval. So it's kind of nice to relate back to the idea of a confidence interval sometimes as we talk about this process. Remember, in a confidence interval, we really have two types of error, right? We have alpha, which is basically the probability that you're incorrect. Like a 95% confidence interval has a 5% chance of error, or a 5% chance of being wrong. But we also have the error tolerance or margin of error, which is what we add and subtract from our statistic in order to create the interval. So we also have that type of error. And the relationship between the error and the confidence interval works very similar in a hypothesis test. So let's just start with some intro stuff. Let's talk about what we do in terms of our hypotheses. So there are always two hypotheses in a hypothesis test. We always start with what we call the alternative hypothesis, and the way that I will set these up for our purposes is basically the hypothesis that we want to prove is what will be called the alternative hypothesis. We denote that by H subscripted with an A. So the alternative hypothesis, the main thing is whenever you read the questions, it's whatever you're trying to prove in terms of the question. Now there are some limitations in terms of what you're able to prove with a statistical test or a hypothesis test. We can never prove equality, which we kind of already know that anyway through probability, because we can never prove in a continuous case that something is equal to a specific value, because the probability of equality, remember, in a continuous case is always 0. So you can't prove equality. So one of the things you'll notice as we go through problems is you'll notice that equality is never part of HA. It can never be part of what you're trying to prove. So that is important if you ever do any thing additional beyond this course with statistics, because whenever you set up these hypotheses, you always want to make sure that you don't include equality as part of your alternative hypothesis. So what that really means is that HA will really be one of three things. Either we'll be trying to prove greater than, or we'll be trying to prove less than, or we will be trying to prove not equal to. Those are really the three things that we will be testing and trying to prove. So that is one of those three things will be your alternative hypothesis for each of the problems in the course. In a hypothesis test, we always have two hypotheses. We also have what's called the null hypothesis, and this is just a hypothesis that contradicts what we want to prove. It contradicts HA. So the null hypothesis is denoted by H subscripted with a 0. We typically call that H naught. So H naught will represent our null hypothesis, which contradicts what we're trying to prove. And of course, since HA never includes equality, H naught always includes equality, and that's important in terms of the setup of how we conduct a hypothesis test. Mathematically, it's very important because basically what we're going to do is we are going to assume that the parameter equals some quantity, and that will be basically assuming that the null hypothesis is true. And then we're going to try to prove that that really could not be the case, that the parameter really could not be equal to that value. It must actually be either greater than, less than, or not equal to that value. Basically, we're going to try to prove that the null hypothesis is wrong, meaning the alternative hypothesis is correct, which is actually why we call it the alternative hypothesis, because we actually test the null hypothesis and try to disprove it, and then alternatively, HA is true, of course, if the null hypothesis is false. So there's some errors that can occur through this process, and probably the easiest way to think about them is just kind of put them all in a table like we have here, and the table's got a lot in it, but this is a good way to think about the mistakes that can be made when you go through this process of a hypothesis test. So what you'll notice if you look at this table is you'll notice if you look down that first column, you'll notice the rows of the table represent basically the outcome for the hypothesis test. So when you conduct a hypothesis test, there are always two possible outcomes. So when you make your decision, you're always going to say one of two things. Either you're going to reject H naught, and if you're able to reject H naught, that means it's false, which means HA must be true. You've proven what you want to prove. So that's really the goal most of the time in hypothesis testing, is you want to reject H naught, meaning the null hypothesis is false, which means HA is true and you've proven what you want to prove. The second outcome is fail to reject H naught. So if you fail to reject H naught, that means you did not get enough information from your sample to be able to reject it. Do notice you never say accept H naught. You can never prove the null hypothesis because of mathematically the way these are set up. I've already said that the null hypothesis includes equality, and that's basically what we're going to assume. And do remember, by probability, we know that the probability of equality is 0. So in a hypothesis test, you can actually never prove H naught. You can never prove equality. Anyway, that first column represents basically the two outcomes from your test, either reject H naught or fail to reject H naught. So that's what those rows represent. If you look at the other two columns, if you look at the last two columns in this table, you'll see that those represent what the actual decision should be. So the only way to actually know whether HA or H naught is true is to actually do a perfect census, have no error, and then you could calculate exactly what your parameter was. And if you actually did this, then of course it would be possible that H naught is either true or false, because for example, if you're estimating the population mean at any given point in time, the mean is a specific value. Now the probability that we get that value exactly right is 0 theoretically, but the mean actually is a specific value. So in reality, H naught is actually either true or false. So that's what those columns represent. The first one you can see there, or I guess it's the second column in the table, represents when H naught is false, and then that last column represents when H naught is true. So based on this, you can think about, well, when am I going to make an error with this test and when am I not? And then we can talk about how we identify these different types of error. And when do we make the correct decision? What do we call those? So let's start with the column where it says H naught is false. So if H naught is false, that means the correct decision would be to reject it, because if something is false, we want to reject something that is false. That would be the correct decision. So you can see in that first column, H naught is false. If you reject H naught, we say that is the correct decision. That's what decision should be made when you conduct this hypothesis test. If you fail to reject H naught, then you've made an error, because if you don't reject something that is false, well, that's the wrong decision. Your test gave you the wrong decision. That's actually what we call a type 2 error. A type 2 error is denoted by beta. Beta is actually the probability of a type 2 error. So when you see that symbol, that's just a beta from the Greek alphabet. That beta represents the probability of a type 2 error. So when you fail to reject H naught, given H naught is false, that's really a conditional probability. That is equal to beta, which is the probability of a type 2 error. That's the way we denote that. You can also see when we make our correct decision there, you can see that when H naught is, or when we reject H naught and H naught is false, that is the correct decision. That is known as the power of a test, and it is actually the complement of the probability of a type 2 error. So it's 1 minus beta, which should make sense. You have the same condition there. You're given H naught is false, so the probability that you reject H naught plus the probability you fail to reject H naught within this category of H naught being false, those have to give you the total probability of 1. So those are complements of each other. So that quantity 1 minus beta is known as the power of a test. The power is technically the probability that you reject H naught when in fact it is false. And if you reject H naught, that means you're able to prove HA. So it's basically the probability that you're able to prove what you want to prove when it is in fact true. So that's an important quantity, actually, and we don't actually calculate it in this class, but I want you to know what it is, because it is a messy thing to calculate. But you want when you conduct a test, the hypothesis test, you want your power to be high, because if what you're trying to prove is actually true, then you want the probability of being able to prove it to be true, to be very high. Because if you have a power of 20%, then what that means is even if what you're trying to prove is true, you're only going to prove it 20% of the time. And that's not what you want. You want to actually be able to prove it's true when you go to collect your data. So the power of a test is important, because the power of a test is basically the probability you're going to be able to prove what you're trying to prove when in fact it is true. So the other part of this table is that last column where H0 is actually true. So if H0 is true and you reject it, of course that is an error. You don't want to reject something that is true. So you can see that first cell, that's your other type of error. That is a type 1 error. A type 1 error is known as your alpha. It's also called the level of significance. So the nice thing about this error is this is really nothing new, because we already talked about alpha when we talked about confidence intervals. For example, if you're 95% confident, that means alpha is 0.05. It's 5%. It's basically 1 minus your confidence level. So whenever you go to do a hypothesis test, it is exactly the same thing. That alpha level will be given to you whenever you're doing problems, and that alpha level will tell you how confident you're able to be if you're able to prove what you want to prove. So in a test, if you have an alpha level of 5%, that means if you're able to prove it, that means you're going to be 95% confident in your conclusion. You're never 100% sure. In inferential statistics, there's always a probability of error. That comes from the fact that we're using a sample to estimate a population, and samples aren't perfect. But we can control the probability of error and make it really small. And that alpha represents basically the probability that you are incorrect in that case, which means 1 minus alpha is basically your confidence level. And you can, of course, see that if you look at that bottom right corner. You can see when H0 is true and we fail to reject it. That's what we want to do. We don't want to reject something that is true, so that is the correct decision, and that is known as your confidence level. That is your 1 minus alpha value. So it's very important to note we have two types of error in hypothesis tests, and this is always the case in inferential statistics. You always have two kinds of error. So here we have a type 1 error and a type 2 error. The probabilities of these are alpha and beta. So I don't want you to lose what you learned in confidence intervals. Remember, in confidence intervals, we had two types of error there as well. We had alpha and E. So alpha hasn't changed. The different thing here is in a confidence interval we had alpha and E, and in a hypothesis test we have alpha and beta. So that alpha really represents the same quantity here. It's the other kind of error that is different. The nice thing, though, is the relationships between these errors are the same. If you remember in a confidence interval, if you decreased alpha, then you would increase E. Basically, if you decreased alpha, you became more confident. To be more confident, you had to have a wider interval, which meant E got bigger. So if you decrease alpha, you increase E. Same thing with the hypothesis test. This is always the way it works in inferential statistics. If you decrease alpha, you're just simply going to increase beta. So it's always this balancing act in terms of if you decrease one type of error, you're going to increase the other type of error, because if you hold everything else constant, that error has to go somewhere. So if you simply decrease alpha, you're going to increase beta. So that inverse relationship between your errors and inferential statistics is a good thing to know. And it holds not just in confidence intervals, but it also holds here in hypothesis tests. So that's kind of the first thing you need to know. You need to have an understanding of kind of what your hypotheses are, know some of the terminology, and then, of course, you need to understand these errors and how they're related to each other. We won't actually calculate the power, but I do want you to know what power is. So most of what we're going to do here is, once you understand the basics, we're going to actually go through the process of conducting a hypothesis test, both for a mean and a proportion for a single sample. At least in this section, we're going to deal with a single sample. So the steps of a hypothesis test. So the nice thing is the steps of a hypothesis test are always the same. Doesn't really matter how messy your analysis gets. We always basically go through the same process to do a hypothesis test. So the first step is just essentially state your hypotheses. So these are what we've been talking about. Always start with HA. HA is what you want to prove. It does not include equality. H0 contradicts what you want to prove. Equality is always involved in H0. Once you do that, in a real study, you would decide what you want alpha and N to be. For our purposes, I will always tell you what alpha and n are going to be in the problem. So you don't have to worry about that part. So the part that I have in parentheses there is the part that will be given to you. But this is where, in a real study, you would specify your alpha level, how confident you want to be. Is, of course, 1 minus alpha. So if you want to be 95% confident, you make alpha 5%. You would also figure out how big a sample you need to take. From that information, you would figure out your critical region. So that will be what you do for step 2 for our purposes, because you're going to be given alpha and n. So the second step will be identify your critical region. The third step, this is where you would actually take your sample. So you wouldn't take your sample until step 3 once you've decided your critical region. Then you take your sample and you compute what's called a test statistic. These test statistics will be nothing new. These will be formulas that you're already familiar with, but these are basically, these are statistics. Remember, a statistic is a numeric characteristic of your sample. So we're going to take a sample, we're going to calculate a value from that sample, and then we're going to compare it to our critical region. It's going to allow us to determine whether or not we're able to prove HA or H naught. And as we go through examples, I'll show you how this works. Step 4 is make your decision. So there's only 2 options for step 4. When you make your decision, you're either going to say reject H naught or you're going to say fail to reject H naught. That's your only 2 options. And then the last step is just simply interpret your results. You want to make some statement in terms of the question about what your results tell you. So that's always step 5. And you'll see how we interpret the results as we go through these examples. Okay, so let's do some examples. So there are a few different scenarios that we deal with. We will start, and this is where you start mathematically in terms of figuring out how hypothesis tests work. Mathematically, what you start with is you start with a simple case where you're making some statement about the population mean, mu, and you actually know what the population standard deviation is. We did the same thing in confidence intervals. Here we're going to use that same scenario where we're doing a hypothesis test for mu, and we actually know what sigma is. Keep in mind, knowing sigma is not realistic, because if you know the population standard deviation, you likely know the population mean, because how else are you going to get the population standard deviation without having the population? So typically we're going to estimate sigma by S, but that's kind of the next step. But for this first problem, we're going to assume that we know sigma. So if we read through this scenario, it says a random sample of 50 monthly rents for 2-bedroom apartments was selected from a certain city. The mean of this sample is $946. Assume the population standard deviation is $124. So do notice we know the population standard deviation. It's important to notice that when you read this, so that is sigma. A group of students think the mean rent for 2-bedroom apartments is more than $900. So that's what we're going to want to test. Test their claim with a significance level of alpha equals 0.05. So we're going to be given alpha. So the first thing that I recommend you do with these problems is just write down what you know. Write down what you know in terms of the test. So here's what I like to do first, and I'm going to just show you what I would write down to start this problem. So we're not going to worry about what we're trying to test yet. That'll be step 1 in terms of the test. But let's write down the numerical values given to us in this problem that we need to conduct this test. So we're going to need the sample size, we're going to need alpha, and then we're going to need the information from our sample. We're also going to need the population standard deviation in this case because we actually know what it is in this case. It's given to us. So n is 50. It says in that first statement, a random sample of 50 monthly rent. So that's your sample size. It tells us that we're going to use the significance level of alpha equals 0.05. And then it also says the mean of this sample is $946. So that's your sample mean. Sample mean is denoted by X bar. That's 946. Then we're told that the population standard deviation is denoted by sigma. That is 124. So this is the information from the problem that we really need, along with step 1 of the hypothesis test, which is what we want to prove. So the first step is always going to be to set up HA and H naught. So the other part of this question that's really important in terms of setting this up is what are we trying to prove? So the problem says a group of students think the mean rent for 2-bedroom apartments is more than $900. So that's what we're trying to prove. We're trying to prove that the population mean is more than 900. So the way we write that, this is step 1, is we write HA. That's our alternative hypothesis. That's what you want to prove. Then we use a colon to separate out what we're trying to actually test. We start with the parameter. The parameter here is mu. That's the population mean, and we want to show that population mean is greater than 900. So that's the way we write it. We write HA colon mu greater than 900. H naught is the contradicting statement. So basically, what contradicts greater than? Well, less than or equal to. So H naught is written the same way. H naught colon mu. We contradict it, so we say less than or equal to 900. So that is what you're trying to prove. So really, that is the information we need from this problem in order to conduct the test. So in order to have enough room on the slide, I'm just going to look at just this information, and we're going to go through the rest of the test. We now have all the information that we need in order to conduct this test. So that is all the numerical quantities we need from the problem, along with what we're trying to prove. Step 2. So step 2 is your critical region. So your critical region is, you always draw a picture. It's also called the rejection region. The critical region gives you the values in which you will reject the null hypothesis. So it's also called a rejection region. So the way that we get this is we know that whenever we are looking at the mean, and we know the population standard deviation, we know that we have a z transformation that gives us a random z value when we take a random sample. So this is going to be a z. When you're interested in the mean and you know sigma, it's always going to be a z. So the critical region is, we're going to start by drawing our picture. We're going to draw a normal distribution, and I have it drawn out here for you so you can see it. So we draw our bell-shaped curve. We know it's standard normal, so we put a 0 in the middle. The other thing that comes into play here is alpha. So alpha is 5%. So we know that the area that we're going to shade is 5% or 0.05. So we look at what area do we shade. So you have two options. It's always going to be the area in the tails that you shade when you do a hypothesis test. So it could be the area to the right, it could be the area to the left, or it could be the area in both. And the way you determine that is you look at what you're trying to prove. So notice, you always look at HA. Notice HA is greater than. So since HA is greater than means to the right. So that means we're going to shade area to the right, and that area is going to be 0.05. So there's basically two main things that you look at here in order to figure out this rejection region. Is you look at what you're trying to prove, you look at the sign, which in this case is greater than. That tells you it's the area to the right. And then you look at alpha. Alpha is the amount of area that you shade, which in this case is 0.05. We can then use our table in order to look that value up. We just look up z of 0.05. The place that I recommend you look this up is, remember, the bottom row of your t-table gives you z values. So the easiest place to look this up is just look up t of 0.05 and look at the bottom row of the table, and you will see that we get a z value of 1.645, because as the t goes to infinity, as the sample size goes to infinity, the t becomes a z. So the bottom row of that t-table is the best place to look these up. So again, look at the bottom row of the t-table where we have 0.05 as our alpha. So that's the area in the tail. That will give you that value of 1.645. So most people just draw the picture, and if you just want to draw the picture for step 2, I'm good with that. So basically anything in that shaded region, anything bigger than or equal to 1.645, those are the values of the test statistic that are going to allow us to say we reject H0. That's the way this works. You can see I also wrote a statement there. I just said reject H0 if z is greater than or equal to 1.645. You don't have to write that statement. You can just give me the picture. The picture says exactly the same thing. You can see it's that area to the right of 1.645 that is shaded. That is step 2. Step 2 is to draw that picture of your critical region or your rejection region. Step 3 is to calculate your test statistic. So this is that z that I just mentioned before. We know this is a z because it's for the mean, and we know sigma. So this formula should look familiar to you. We already know that this is a z value. We take x bar minus mu over sigma over square root of n. That is a standard normal distribution, which is why our picture is standard normal. This one's pretty straightforward. You really just plug in what you know. There is one thing you got to be aware of, but for the most part, we plug in what we know. So we know x bar, we're given that, that's 946. The only thing that we don't know in this equation is we don't know the population mean mu. So you have to know what to do here. So what you plug in for the population mean is whatever you're comparing it to. So notice in step 1, we're comparing the mean to 900. So we are going to assume that the mean equals 900. And actually, some people will just write h naught as mu equals 900 because really that's what we're assuming. This is part of the reason why it's so important that equality is always part of the null hypothesis, because that's what we're going to assume. We're going to assume that the mean equals 900, which is assuming that h naught is true. We're going to assume that mu equals 900. And then we're going to try to say, well, that couldn't really be the case. It must not really be 900. It must be something bigger than 900. But to start, you assume that the mean is whatever you're comparing it to. So for the mu, you plug in 900, and then everything else is given to you. The standard deviation sigma is 124, and then the sample size is 50. So we plug that in, we get our test statistic, crank through the math there, you'll get 2.623. So that is step 3. Step 4 is simple. If you get step 2 and 3 right, all you have to do is say, is that test statistic, that 2.623, is that in my rejection region? So if you look at your picture, you can see that 2.623 is bigger than 1.645. It is definitely in that shaded region, which means my decision is to reject h naught. So that's all you have to do for step 4, is you see if your test statistic is in your rejection region. If it is, you reject h naught. If it is not, you fail to reject h naught. So here we do reject h naught. Technically, it's because 2.623 is bigger than 1.645. Then our last step is our conclusion. So we just said we reject h naught. So when you reject h naught, that means that we can conclude that HA is true. So if h naught is false, the mean's not really less than or equal to 900, then we must be able to prove that the mean actually is greater than 900. So we can conclude with 95% confidence. It's 95% confidence because alpha equals 0.05, so make sure you include that. Conclude with 95% confidence that the mean rent for 2-bedroom apartments is more than $900. So your statement just needs to relate back to what you're trying to prove, and you just want to say here that we're able to conclude that with 95% confidence. So that's the way a hypothesis test works. All these work the same way, so it's really just a matter of getting this down, getting this pattern down, and then being able to fit in the details depending on the scenario that you're dealing with. So this is the way that we will do all of our hypothesis tests. We will use these 5 steps. I do want you to be aware, however, of what's called a p-value. And I want you to be able to interpret a p-value, and I want you to be able to calculate it in these simple scenarios where we're estimating the mean and we know the population standard deviation. So a p-value. There's another approach to doing hypothesis tests, and the reason why p-values are important is if you ever take a more advanced statistics class or take a class that's more applied where they just use software to do hypothesis tests, what will happen is the software will give you what's called a p-value. P stands for probability. This is basically nothing more than a probability value. And what you do whenever you can use software and it gives you a p-value is you basically just compare your p-value to alpha, and that allows you to make your decision. So a p-value is just another way to make your decision. So what a p-value is, or what this probability value is it is the probability that corresponds to your test statistic. So let me just show you in this case what the p-value would be. So our test statistic is 2.623. I'm going to have to round that so that we can use the standard normal table. The standard normal table is only accurate to 2 decimals, so I'm just going to use 2.62 to look this up. But basically, you can see our picture there at the bottom. The picture looks very similar to the first one, but the difference is along that, it's really a z-axis there. Along that axis, you can see that I have that value of 2.62 out there, and since I'm trying to prove greater than, I'm just looking at the area to the right of that test statistic, 2.62. So that is my p-value. That's what a p-value is. It's the probability that corresponds to your test statistic. Mathematically, that's what it is. So in order to calculate that, if I look up 2.62 in the standard normal table, it's going to give me that 0.4956. So the area between 0 and 2.2 and 2.62 is 0.4956. So to get the area that I want, the area in the tail, I just take 0.5 minus that. We did this before. That'll give us the probability or the p-value of 0.0044. So the p-value here is 0.0044. So in order to make your decision with a p-value, what you do is you just simply compare your p-value to alpha. So you compare your p-value to alpha. If your p-value is less than or equal to alpha, that means you reject H0. And if your p-value is bigger than alpha, then you fail to reject H0. So you can see here my p-value is 0.0044. That is less than our alpha of 0.05. So that means my decision here based on the p-value approach would also be reject H0. Your decision is going to be the same no matter which approach you use. And the reason being is because the p-value of 0.044 is less than or equal to my alpha of 0.05. If you compare these two pictures, you can see how this works. It's really just a question of what you're comparing. In the approach that we will commonly use in class when we do these by hand, we're basically comparing the z-values, which is the values given along the axis there of 2.62 is bigger than 1.645. In the p-value approach, we're essentially just comparing the areas. But we're doing the same thing. Notice that if 2.62 is in that rejection region, then that means the area or the p-value there has to be smaller than alpha. So whenever you say we're rejecting H0 if the p-value is less than or equal to alpha, that's the same thing as saying basically that this test statistic is within the rejection region. So it's really doing the same thing. It's just a matter of, am I comparing the area or am I comparing the z-values? But you're doing the same thing. When you do this in software, though, for most people who don't go through all the steps and they just get the p-value, it's very easy to compare it to alpha because alpha is a quantity that people understand. But whenever you go through this whole process, not everyone is going to know what the z-value represents, and not everyone is going to know how to get the critical region. But you're really doing the same thing when you compare alpha to the p-value, so it's a commonly used whenever people just use software and they're not actually going through the entire process of conducting a test. So you should be able to calculate a p-value for this scenario. You should know how to interpret it in terms of the decision, what it represents. That just represents a probability value. But the p-value approach is not the approach we'll typically use in class, but I do want you to understand what a p-value is, and you may see it in a class you take later on in your college career. Okay, let's look at another example. So this one is the more realistic case. This one is where we're making a statement about the population mean, but for some unknown standard deviation. So we don't know the population standard deviation, so we're going to have to estimate it with the sample standard deviation. So this one works the same way as the last one, other than instead of having the population standard deviation, we now have the sample standard deviation. As we talked about with confidence intervals, what this means mathematically is this means our z distribution now becomes a t distribution. But other than that, it works the same. So let's go through this one. Suppose we want to prove that the mean commute time for people in Lexington to get to work is less than 20 minutes. A random sample of 15 people yield a sample mean of 17.9 minutes and a sample standard deviation of 7. Is there enough evidence to prove the claim with alpha equals 0.10? Okay, so let's first just write down what we know from the problem. So we know we're taking a random sample of 15 people, so n is 15. We're given that our alpha level is 0.10. We also need the mean. This says the sample mean is 17.9. It also says the sample standard deviation, so that's important. This is not the population standard deviation. So this is the sample standard deviation is 7, so we denote that by S. Remember, if you know the population standard deviation, you denote that by sigma. That distinction is important because if you know sigma, you use the z distribution. If you know sample standard deviation, which is the more common case and the one I typically give you, if you know the sample standard deviation, then that means you're using a t distribution. Of course, the other important part of this problem is what are we trying to prove? So you get that from the first sentence where it says we want to prove that the mean commute time for people in Lexington to get to work is less than 20 minutes. So we want to prove that the population mean is less than 20. So we write that the same way as we did in the last problem, HA colon population mean mu less than 20. H naught contradicts that, so the contradicting is of course just greater than or equal to. So again, to clear up some space, here's the information that we need to complete this problem. Second step, critical region. So the big difference in this problem as compared to the last one is this problem we're trying to prove less than. That means the shaded area is to the left. We also know that that area is going to be 0.10 because that's my alpha level. So your picture is going to look like this. We now have an area to the left that we're going to shade. That area is going to be 0.10 because that's our alpha level. So if you look up this in the table, you do have to keep in mind that you now have to deal with degrees of freedom because this is a t-distribution. So n equals 15, which means we have 14 degrees of freedom. So you got to look up a t with 14 degrees of freedom, and you look up the area in the tail of 0.1. If you look that up, you will get a t value of 1.345. Since we're on the left side of 0, that means our value is negative, so that means we get that value of negative 1.345. We are going to reject the null hypothesis if our test statistic is less than or equal to negative 1.345. Again, you can just give me that picture if you want, but you can also see that I have it written out there as a statement. The third step, test statistic. So you've seen this test statistic before as well. This is just your t. Notice the only difference between this one and the z is we replace sigma by s, and when we replace sigma by s, our z becomes a t. We plug in what we know. We know x bar is 17.9. Again, remember what we plug in for mu. We're comparing mu to 20, so we are going to assume that the population mean is 20. So we plug that in. It's important you remember where that comes from. Standard deviation is 7. N is 15. Crank through the math there, and you get a t-value of negative 1.162. So notice, if you compare that t-value to your critical region, it is not in the critical region. Negative 1.162 is not in that shaded region in your picture, which means in this case, our decision is we fail to reject H naught. If your test statistic is in your critical region, then you reject. If it's not, you fail to reject. So here we must fail to reject H naught. And technically it's because that test statistic is not within the critical region, so basically negative 1.162 in this case is greater than negative 1.345. It's not less than or equal to. Step 5, your conclusion. So when you fail to reject, you're very limited in terms of what you can say. We really can't conclude anything when we fail to reject, and the big reason is there's multiple reasons why we might fail to reject. We might fail to reject because what we're trying to prove is actually not true. But we might also fail to reject just because we didn't get enough information from our sample. Like we only took a sample of size 15 here. So maybe if we took a larger sample, we would actually be able to prove it, and maybe it's actually true. But we took a really small sample here, so because we didn't get enough information from our sample, we're not able to prove it. This could be a case where there's not enough power in our test, and that's why that idea of power comes into play. Even if what you're trying to prove is true, it's not a guarantee that you're going to be able to prove it. With a bigger sample, we could increase our power, and maybe we would actually be able to prove this. But given what we have here, we're not able to prove this. So all we can say in our statement is when you fail to reject, you just want to say something like, there is not sufficient evidence to prove what you're trying to prove. So your statement should look something like this. Just start with, there is not sufficient evidence to prove, and whatever it is you're trying to prove. So in this case, there's not sufficient evidence to prove that the mean commute time for people in Lexington to get to work is less than 20 minutes. So it doesn't have to be that word for word, but it should be something like that. Okay, let's look at another example. A book about college reports that the mean time students study each week is 1,015 minutes. A dean says she believes the mean is not equal to 1,015 minutes. Suppose she takes a random sample of 30 students and finds that the mean is 1182. Standard deviation is 143. So since this is found from the sample, this is the sample mean, sample standard deviation. We're going to test the dean's claim at alpha equals 0.05. So let's write down what we know. We know the sample size is 30, alpha is 0.05. The sample mean is 1182. The sample standard deviation is 143. What are we trying to prove? The dean says she believes the mean is not equal to 1,015. So that's what we're trying to prove. So this is kind of our third scenario. We did one hypothesis test for greater than. We did one for less than. This is your other kind of hypothesis test where you do a not equal to. So this is not equal to. So we write HA colon mu not equal to 1,015. H naught just contradicts that, so H naught is your equality. Okay, so let's give ourselves some space and let's go through the process of completing this problem. So your critical region. So a not equal to. Not equal to is a little different than the other ones because not equal to means you have two options. Not equal to means it could be bigger than 1,015 or it could be smaller than 1,015. So now we're not just specifically testing greater than and we're not specifically testing less than. Instead, we're testing basically either one. It could be greater than or it could be less than. So when you do this, this actually becomes a two-tailed test because now it could be greater than or less than, so we now need area in both of the tails. So you can see alpha is 0.05. That means we have a total error of 0.05. So this one becomes like confidence intervals where we have a two-tailed test. So we want to divide that area in half and put half of it in each tail. So your picture is going to look like this. This looks very similar to what we did with confidence intervals. A two-tailed a two-tailed hypothesis test, the error is set up the same way as it is in a confidence interval. So you can see that we put alpha over 2 in each tail. So alpha is 0.05, so we put 0.025 in each tail. So this is a T because we know S. This is a T with 29 degrees of freedom. Remember, you take n minus 1. A T, 29 degrees of freedom with 0.025. If you look that up in the table, you'll get 2.045. So we're going to reject the null hypothesis if our test statistic is less than negative 2.045. That's the less than part. Or if it's greater than or equal to positive 2.045. So that is our rejection region. Your rejection region when you test not equal to is always two-tailed. You divide your alpha in half in these cases. Okay, our test statistics. So of course that works the same way. We just plug in what we know. We know the sample mean is 1182. Remember, we're assuming that the mean equals 1,015. That's what we're comparing mu to. So we plug that in for mu. S is 143. Sample size is 30. We plug that in. We get a test statistic of 6.396. Fourth step is our decision. 6.396 is definitely bigger than 2.045. It's definitely in the shaded region. Therefore, we reject H naught. Since we reject H naught, we can say H naught is false, which means HA is true, and we have proven the dean's claim. Conclude with 95% confidence. It's 95% because alpha is 0.05. Conclude with 95% confidence that the mean time students study each week is not equal to 1,015 minutes. So we're able to prove this here. So let me just talk a little bit about why this process works. So hopefully you're getting the process down at this point, but let me talk a little bit about what we're really doing here and why it works. So the key to any hypothesis test is that test statistic. So like in this case, you get a test statistic of 6.396. So one way to think about this, think about what's the likelihood that by random chance I get a value that is 6.396 standard deviations above the mean, because that's what that is. That tells you how many standard deviations this is above or below the mean. So this test statistic that I get tells me that I'm 6.396 standard deviations above the mean. So we know by what we've talked about with probability that that is very unlikely to happen by random chance. And that's where this starts, is you calculate that test statistic and you say, how likely is that to happen by random chance? And in this case, we can say, since it's in that shaded region, we can say this has less than a 5% chance of happening by random chance. So we can be 95% sure this did not happen by random chance. So that's kind of the first part of this. We can be 95% sure that that t-value did not happen by random chance. Then you got to say, well, if it didn't happen by random chance, why else could it have happened? And there's only one other explanation to this because of the way we set it up. Notice if you look at that t-value, notice everything in that t-value, we know what it is because we took the sample mean. We calculated the sample standard deviation. We know the sample size. We know all that stuff. But there's one thing we don't know. We do not know what the population mean is. What did we do? We just assumed that H0 was true and that the mean equaled 1,015. But we don't know that at all. We just assumed that. So basically the way it goes is if this test statistic did not happen by random chance, the only other way it could have happened is because our assumption was incorrect. We assumed that the mean was 1,015, but that could not really be true. At least the probability of that being true is less than 95%. It's really small because we got such an unusual test statistic that we know that this probably did not happen by random chance. So if this did not happen by random chance, the only way it could have happened is because the mean is not actually 1,015, and if the mean is not actually 1,015, then I'm able to prove HA, which is that the mean is not 1,015. That's the way this process works. You assume H0 is true. You assume that the mean equals some quantity. And then you try to say, well, that doesn't seem reasonable because the probability or the test statistic is showing that the probability that this would have happened by random chance is really, really small. So it probably didn't happen by random chance. And if it didn't happen by random chance, the only other way it could have happened is because what you're trying to prove is true. That's the logic of a statistician, and that is the way this process works. So when you get these unusual z-values, something like 6.396, that's very unlikely to happen by random chance. That's whenever you're going to be able to reject. There's one other thing I want to do with this problem. I just want to mention how it's related to a confidence interval. Because what you'll notice with the critical region here is you'll notice that the error in these two-tailed hypothesis tests is the same setup as the error in a confidence interval. So what you can notice is you can notice that there is a relationship between confidence intervals and hypothesis test. And we almost treat these things as two totally separate methods, and in a sense they are. But they are very related because they're both based on the same underlying sampling distribution. So I like to make sure that you understand the relationship between the two. This only works when you're testing not equal to, because that's the only time that your error is set up the same way in a hypothesis test and a confidence interval. But in a case like this, you can actually calculate the confidence interval. So let's just do a 95% confidence interval for this data. You can actually tell what the decision of the hypothesis test is going to be by looking at the confidence interval. So 95% confidence interval for this data. I'm not going to spend a bunch of time on it. We did that in the last section. But if you calculate it, this is what you'll get. You'll get 1128.609 to 1235.391. That is the confidence interval. So we're 95% confident that the population mean is between those two values. Well, if you look at that confidence interval, what you'll notice is the confidence interval and outcome to the hypothesis test are always going to be consistent. So if you look at that confidence interval, what you'll notice that the value that we tested in the hypothesis test, 1015, is not in that interval. That entire interval is above the value of 1015. 1015 would be to the left of those two values in the confidence interval on the real number line. So 1015 is not in that interval. So that means if we're 95% sure that the mean is between 1128.609 and 1235.391, we are also 95% confident that the mean is not 1015 because 1015 is not within the interval. So you can actually tell the outcome of this hypothesis test based on the confidence interval. The confidence interval actually gives us more information in a case like this because it actually gives us a range for which the mean would be within, not just that it's not equal to 1015. So in these kind of cases, lots of times we're more interested in the confidence interval, but sometimes there are situations where the hypothesis test is more useful, and in some situations there are even things that we test that there's not really a good equivalent confidence interval for. So it's important that you're familiar with both methods of a confidence interval and hypothesis test, and it is nice to see the consistency between the two whenever you set up the error the same way. Remember, the error is set up the same way when your hypothesis test is two-tailed. Basically, you're testing not equal to. One other type of problem that we're going to deal with in this section is we will also estimate or perform a hypothesis test for a proportion. When you're testing a proportion, because of the way standard deviation works with a proportion, we actually need large samples because, with the mean, whenever we replace sigma by s, the z becomes a t. We don't have that equivalent scenario with a proportion. So with a proportion, we always have to use a z because no one's figured out how to model it when you replace basically the sample standard deviation for the population standard deviation. It hasn't been exactly figured out. So a large n is usually not a concern anyway when you deal with a proportion, but with proportions it is very important that you have a large n so that just like with the z distribution becoming with the t distribution becoming a z as n becomes large, it works the same way here. Basically, as n becomes large, you can just use the z distribution. It really doesn't matter. So proportions, it is important that you have large samples. Anyway, the scenario is this, or the question is this. A marketing manager for a cell phone company claims that more than 45% of children, age 10, have cell phones. In a random sample of 500, it found that 231 had cell phones. Can you conclude that the manager's claim is true? So again, start with what we're given in the problem. So the sample size is 500. We take a random sample of 500. Alpha is given to us at 0.01. We also need the sample proportion. Remember, the sample proportion is denoted by p hat. So p hat says, p hat is the proportion which is from the problem. In a random sample of 500, it found that 231 had cell phones. So that means 231 out of the 500 had cell phones. That's 0.462 or 46.2% of my sample. So now we can look at what we're trying to test. Here we're trying to test, the claim is that more than 45% of children have cell phones. So that means we're trying to prove that our proportion is greater than 45%. So notice this is very similar to the mean, but do be careful. Don't write mu because this is no longer a mean. This is now our proportion. So make sure you pay attention to your parameter. So we still write it the same way. We write HA colon, but now instead of writing mu, because this is not a mean, this is a proportion. So we write the population proportion P. And we want to show that P is greater than 0.45. So that's the way we write it. H naught just, of course, contradicts that. So that's the information we need from the problem. So let's go through the rest of the process. So we just said that proportions are always standard normal. So we're trying to prove greater than, which means the area to the right. We also know that alpha is 0.01. So we shade that area to the right to be 0.01. If, again, look at the bottom row of the t-table, that'll give you the z values. If you look up 0.01, bottom row of the t-table, you'll get the z to be 2.326. So that means we're going to reject the null hypothesis if our test statistic is greater than or equal to 2.326. Your test statistic for a proportion, and you've seen this before as well, is p hat minus p over the standard error is the square root of p times q over n. So we plug in what we know. We know p hat is 0.462. Remember what we do for p. P is 0.45. We're assuming it's 0.45 because that's what we're comparing it to in our hypothesis. We're going to assume that p is 0.45. Q, you have to remember that q and p are always complements of each other. P is the proportion. Q is the complement of the proportion. That's the way it always works. Actually, the variance over proportion is p times q. So that's where that p times q comes from. Then we plug in n of 500. and we crank through the math there, we get a test statistic here of 0.539. Step 4, you compare your test statistics to your critical region. You can see that 0.539 is not in our shaded region. That means we must fail to reject the null hypothesis. If you were able to reject here, we would be 99% confident because alpha is 0.01, but we're not able to reject, so you can't really say much here. Remember, when you fail to reject, you're going to say there's not sufficient evidence to prove what you're trying to prove. So here you would want to say something like, there is not sufficient evidence to conclude that more than 45% of children age 10 have cell phones, something like that. So that does wrap up this section. The big thing in this section, of course, you have to know the intro stuff. Like we talked about at the beginning, you got to know some of the terminology, what the different hypotheses are called. You have to know how the errors relate to each other and what the errors are. But the big thing is just being able to work through these problems. As you work through these problems, there's some important things to note. Remember that when you set up your critical region, you're looking at your alpha level tells you the area. What you're trying to prove, HA tells you where the area you shade is going to be. If it's greater than, it's the area to the right. If you're trying to prove less than, it's the area to the left. If you're trying to prove not equal to, it's the area in both tails. Then make sure you get your proper test statistics. So there's 3 test statistics that we deal with in here. We deal with the Z whenever you're looking at the mean for a known population standard deviation. Then we use the T for the mean whenever we don't know the population standard deviation, and then we use the Z as you see here in step 3 for the proportion. So that test statistic is important. There's 3 different ones that you'll use in this section. And then know how to, of course, determine whether or not you fail to reject or you reject. Understand what a p-value is. And I think those are the big things in this section. But of course, you got to be able to work through these hypothesis test questions. That's the main thing. So anyway, that is the end of section 9.